I can say the 12 Cartesian coordinate three-dimensional source term unsteady state problem. For I can say the 12 Cartesian coordinate three-dimensional source term unsteady state problem, and then the task becomes simple. It is a unsteady state three-dimensional heat conduction with a finite source term. Of course, as a modeler, you have to now provide an expression for ST. You must understand that this represents only one equation, and hence we can at the most have one unknown, and the unknown here is the temperature, which, as the equation indicates, is a function of x, y, z, and t. So we will have to have some expression. For the source term, and this source term itself may be temperature dependent. If you remember the iron carbon phase diagram, then you can see, you can look at the tie lines and find out that the proportion of austenite will change depending on what temperature it is. So therefore, this ST is actually a function of tie. So therefore, this is a non-linear heat source term. Because unless you know the temperature, you will not be able to predict or solve this particular equation. So as far as the formulation is concerned, we can now formulate the problem. I'm going to come back to it. But note that because we are talking of mechanistic model, and that I said mechanistic models are going to give rise to partial differential equation always, we have to not only write down the equation, but we have to provide the boundary condition also.
Por la frontal, Isco dentro del área, qué buena la de Isco, sigue Isco, Isco.
walking alone. Set my heart afire.
Shout out another. Si Ilocano ngayon pang muli. Maganda.
It is. The formulation essentially implies that we have to write down the governing equation, we have to write down the corresponding boundary condition, and then only the statement of the problem is complete. Then only we have to write the condition. Essentially, equation always we have to not only write down the equation, but we have to write the boundary condition also. This the formulation essentially implies that we have to write down the governing equation, we have to write down the corresponding boundary condition, and then only the statement of the problem. Problem is complete, then only we can say that yes, we have been able to formulate the problem correct. This exercise can be taken, for example, in the context of a ladle metallurgy. You can say that, well, I have a ladle gas injection procedure, and what I want to model there, well, I have added a ferroniobium solid, and I want to find out that after what time ferroniobium gets completely dissolved in that. steel bar. So your problem definition is complete. Now you have to look at, well, the slag contains, next we go to the conceptual modeling. It is a cylindrical system, okay, but the plug is located away from the axis of symmetry, so it's a three-dimensional problem basically. But it is a multi-phase problem. I have gas injection, I have a slag layer, I have melt. Do I solve it as a multi-phase problem? Do I solve it as a steady state problem or an unsteady state problem? So all these questions you are going to ask, and then you can say that, well, I can, having conceptually modeled the situation, I can say that because dissolution is a mass transport phenomena, I have to have, the flow in the system known, so therefore I have to solve the fluid flow equation. Having obtained the fluid flow equation, I will solve the mass transport equation because dissolution is a mass transport phenomena, and that is the way we are going. I can, having conceptually modeled the situation, I can say that because dissolution is a mass transport phenomena, I have to have, the flow in the system known, so therefore I have to solve the fluid flow equation. Having obtained the fluid, I have to have, the flow in the system known, so therefore I have to solve the fluid flow equation. Having I have to have, the flow in the system known, so therefore I have to solve the fluid flow equation. Having obtained the fluid, having conceptually modeled the situation, I can say that because dissolution is a mass transport phenomena, I have to have, the flow in the system known, so therefore I have to solve the fluid flow equation. Having obtained the fluid flow equation, I will solve the mass transport equation because dissolution. So therefore I have to solve the fluid flow equation. Having obtained the fluid flow equation, I will solve the mass transport. Equation because dissolution is a mass transfer phenomena, and that is the way we are doing. Having obtained the fluid flow equation, I will solve the mass transport equation because dissolution is a mass transfer phenomena, and that is the way we are going to calculate the problem. Once you write the conservation of momentum or fluid flow equation, conservation of mass of the mass transport equation, we will write the boundary condition. Again, we say yes, we have been able to formulate the dissolution of ferroniobium in steel in a realistic manner because we have been able to write down the corresponding equations, but differential equations, which we call as the governing equations, together with the boundary conditions. Once we have mathematical model formulation, and then we are going to solve this equation. Solution. This is very important for us, and we'll discuss this in detail later on. Solution, because these partial differential equations, in most of the cases, you will not be able to solve analytically. Analytically means, suppose you have solved many differential equations, okay, the non-homogeneous equation, you have then you have written complementary functions and simple ordinary differential equations, even unsteady state equations also through product solution techniques, error function solutions techniques can be solved by hand, but these equations cannot be solved by hand. Okay, so you will not.
Waiting for
not be able to solve analytically, which means if you give given a pen and paper, you will not be able to solve these equations. You have to resort to numerical technique.
Something to hold on to, gotta find it first. But here I am, 'cause I've been laying under palm trees, waiting for the summer, knowing there's nowhere to go. 'Cause I am happy on this island, wanna be my farmland. I don't ever want to leave, I'm in a tropic club.
To solve this equation. What does a numerical technique do? A numerical method basically converts an algebraic differential equation into a set of algebraic equations and then we solve the equation. So the purpose of the numerical method is to convert a given differential equation into the corresponding algebraic equations, and then we require, once we have a set of algebraic equations, large number of algebraic equations, then of course we require a digital computer, otherwise we will be taking very, very long time to solve this. So the set of algebraic equations can be solved with a suitable solution, algorithm, or a computer platform or computer program, whatever you may say. So, partial differential equation PDE, and this gets to algebraic equation in solution. Not just one algebraic equation, many algebraic equations it gets to, and between the two, what connects the two is the numerical method. One important point I would like to say, that there are innumerable numerical methods available by which you can translate a partial differential equation into so therefore, the form of the algebraic equation is going to be different depending on what kind of a numerical methods you have applied to translate this differential equation into equations. For example, if I take a differential equation, use Taylor series approximation, I will get one type of algebraic equations. If I use a different kind of algorithm, for example, if it's an ordinary differential equation, there are innumerable algorithms. Like I can consider Runge-Kutta method, I can consider Runge-Kutta-Gill method. Second order method. Fourth order method, Adams-Moulton method. So many. And in each cases, the final algebraic equation looks different. So therefore, the solution of the algebraic equation are also going to be different depending on what sort of numerical methods we apply. But we must understand that the partial differential equation together with the boundary condition defines the problem explicitly, which implies that we have to have a unique set of solutions. Now, since I have said that different numerical methods will produce different algebraic equations and hence different solutions, this seems to contradict my statement, but mind it that eventually in algebraic solution, because when you write down the algebraic equations, convert the differential equations into algebraic equations, we solve the equations at discrete location in the system, which we call as the various nodal points. So when the large nodal points are used in the system,
Open eye, feel the waves cut through me, hypnotized by the sounds I'm breathing in. Hold tight,
or the resultant number of algebraic equations very, very large, in that case, the solution, despite having different numerical methods, is going to be identical, and that solution basically we talk about the grid independence. So when you do mathematical modeling, it is very important for us to establish a grid independent solution, which is the meaningful solution, which is the reflection of the solution of the differential equation together with its boundary condition. So we solve the equation, and we can try now to get certain asymptotic solutions for which I have an analytical solution. For example, I have a three-dimensional equation that I have taken. Now, if I set this term to be equal to 0, consider that this term is going to be equal to 0, that's a steady state phenomena with no heat source. Then I have, it's a pure steady state heat conduction in 3 dimensions. And if I now say that, well, all surfaces are fixed at certain temperature, a benchmark situation, which has nothing to do with the problem, I am going to, because I solved the equation, but I have to understand and I have to know also that this conversion is correct, algebraic equation, and the solution that I am going to get is a meaningful solution to correct solution. How do I test it? So under certain limited or asymptotic situation, I am going to solve these equations, and a typical benchmark solution or the limiting situation is
hold tight, chemicals collide. Hold tight, dripping light.
I am going to meaningful solution to correct solution. How do I test it? So under certain limited or asymptotic situation, I am going to
Dripping lights paint the skies. Only you can make me move. You can make me move. Can make me move. Can make me move. You can make me move. Can make me.
meaningful solution to correct solution. How do I test it? So under certain limiting or asymptotic
Open eye, feel the waves cut through me, hypnotized by the sounds I'm breathing in. Hold tight, chemicals collide. Hold tight, hold tight, hold tight. Dripping lights paint the skies, all because of you. Dripping lights paint the skies. Only you can make me move. You can make me move. Can make me move. You can make me
solution that I am going to get is a meaningful solution. How do I test it? So under certain limiting or asymptotic situation, I am going to solve these equations, and a typical benchmark solution or a limiting situation is that we write down the complete model for this, okay, based on the conversion and the solution techniques. And we say that, well, in the computer programmer platform, let us set the source term to be 0, let us consider a steady state situation. By considering this equal to 0, we then find out that the problem confers to a steady state three-dimensional scenario, and then if we further assume that all surfaces are maintained at a constant temperature, need not be same. Okay? In that case, an analytical solution to this particular problem is possible, which is given in standard heat conduction textbook. So I can run my computer program, I can solve the equation, and for this particular limiting situation, I can compare with my textbook solution. Okay, so then I can say, well, there is a reasonable certainty that the programming that I have done is correct, because it is able to replicate many such solutions which are given by other people or other sources. We can also say that, well, I am not the first person to solve this equation. There will be many other people who have solved these equations for certain different cases or different boundary conditions. Okay, so I can also run my computer program or run my solution of the differential equation for certain situations which have been relatively well investigated and reported by various investigators. Differential equation for certain situations which have been relatively well investigated. Reported by previous investigators, and then I can say that, well, I have developed a computer program. The computer program produces estimates of temperature that agree well with those reported by various other investigators. So I have some confidence that yes, the computer program solution methodology that I have developed following problem definition, conceptual modeling, and to the program solution methodology that I have developed following problem definition, conceptual modeling, and mathematical formulation is indeed correct and is reasonably estimate. So, having obtained some confidence about the numerical solution technique, now I am going to bifurcate, and at one string I am going to now run this program in its entirety. Now, no more asymptotic solution. So, I am going to use the exact equation which I have written. I am going to write down the exact boundary condition, what type of boundary conditions are there. Of course, I am not talking about it, but you know that every differential equation will have certain boundary conditions and initial conditions. For example, if you do a simple second order ordinary differential equation, if you integrate that, you will get two constants of integration. How do you derive those constants of integration? You obtain these constants of integration from the boundary condition. So similarly, we will have 7 boundary conditions attached to it. There is a second order term, 2 conditions on x, 2 conditions on y, 2 conditions on z. Then 1 condition is d. So with 7 conditions embedded, I should be able to solve the exact problem that I have been able to identify in the beginning. So I can solve the problem. Industrial simulation. At the same time, I have been able to, when I do industrial simulation, I have been able to find out that, well, the inside temperature is this, outside temperature is this at various times. So I want to check whether my results are correct or not. So parallelly, along with industrial simulation, I can carry out some experiments. So I can use techniques to determine the surface temperature, for example, and then I can compare them. So these experiments can be carried out, for example, maybe with a contact pyrometer or maybe with an optical radiation pyrometer. So I can measure from distance what is the surface temperature at certain time. The model can also, or maybe with an optical radiation pyrometer. So I can measure from distance what is the surface temperature at certain time. The model can also predict, once you do the exact simulation of the industrial process, that time temperature history at various locations. So this comparison will give us an idea that whether our model is accurate. As I have mentioned to you, that there may be many assumptions involved in formulating the governing equation and formulating the boundary conditions. For example, this heat source stance, we can make various kinds of an approximations, okay, in order to formulate that how the heat is divided because of the solid state heat transformation equation. Also, I can formulate, as I say, that the transport of heat from the surrounding to the surface, whether it is by convection, whether it is by radiation, what is the heat transfer coefficient, what is the emissivity of the surface, many assumptions may be there, okay, many idealizations may be there. So we are not expecting that there is going to be one-to-one correspondence between the experience and industrial simulation. So there is going to be some amount of uncertainty, and therefore it is realizations may be there. So we are not expecting that there is going to be one-to-one correspondence between the experiments and industrial simulation. So there is going to be some amount of uncertainty, and therefore it is always desirable, as I have mentioned, that models without measurements are incomplete. So therefore, in any sensible investigation, we have to have parallel experiments and simulations. simulation experiments as well as the model simulation, and this will give us some idea that how realistically we have been able to formulate the model in the boundary condition. At this particular point, we may find that well, some tuning may be necessary because we have done some made some assumptions and some idealizations. So therefore, there is some discrepancy or differences between this and this. So in order to match the predictions with experiments oriented, we state force fitting. So now we find out that well, say at a given location, this is time, and t at certain location, capital X, okay, y, z, and certain time t1. So at certain specific location, capital X, at certain time t1, suppose I find that, or I could say that no, it varies as a function of, at a location of x, capital X, as a function of y, z, and z. So I can say that at this particular location, suppose the temperature varies something like this. This is my prediction. I would write it like this. Say, let us fix y, let us fix z as a function of x. So that's what. Okay, the fixed value of y, fixed value of z as a function of x and t. I am talking about temperature. So this is actually t at a location x is a function of time. So this is my prediction, and I can find that well my measurements are going to be. Okay, in that case, it may be possible to do some tuning and bring all the points a little bit closer. Okay, and I can find out that well now my points have become like this. So I'm forcing the points. These are actual observations, and I'm forcing the points to correspond to the actual the prediction. And this has happened. This difference has happened between this is the actual measurements. Measurements And what are the reasons for this difference? That my actual measurement is here, while the line goes something like this, and the actual measurements are different from the line because of the fact that we have some idealization and simplification in formulating the model. So I wish to. Now this is not going to be a very realistic model. So therefore, I want to bring. These are the actual measurements. So I want to bring this. For example, I can say that is basically I can move this line a little bit here. So let us. So these are my actual measurements. These are my actual measurements. And this is the line that I have predicted. So there is evidently some difference between the experimental points and the model line. Now, I cannot say these are actual measurements. So these points cannot be altered. Okay? But I can change the model. From here, the line can go, I can bring it here by changing certain parameters, for example, changing thermal conductivity, changing boundary condition.
the sky, gazing far into the night. I raise my hand to the fire, but it's no use, 'cause you can't stop it from shining through. It's true, baby, let the light shine through. If you believe it's true, baby, won't you let the light shine through for you, 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 won't you let the light shine through? Eyes in the sky, gazing far into the night. I raise my hand to the fire, but it's no use, 'cause you can't stop it from shining through. It's true, baby, let the light shine through. If you believe it's true, baby, won't you let the light shine through for you, 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 for you.
conditions, changing source term, I should be able to change the prediction, take it up, take it down. So this is called, this stage of bringing the prediction closer to the reality is termed as my actual measure. These are the actual measures in formulating the model. And this difference has happened between and I can find out the 12, now my point, or okay. In that case, it may be possible to do some tuning and bring all the points a little bit close. Okay. And I can find out the 12. Now my point has become like this. So I'm forcing the points. These are actual observations, and I'm forcing the points to correspond to the actual or the prediction. And this is happening. When this difference has happened between, this is the actual measurements, and what are the reasons for this difference? That my actual measurement is here, while the line goes something like this, and the actual measurements are different from the line because of the fact that we have some idealization and simplification in formulating the model. So I wish to, now this is not going to be a very realistic model, so therefore I want to bring this changing thermal conductivity, changing boundary conditions, changing source term, I should be able to change the prediction, take it up, take it down. So this is called, this stage of bringing the prediction closer to the reality is termed as the force fit. Or so this is the tuned model. So in many cases, model tuning is going to be necessary because we have made certain amount of idealizations, and so once this, whether tuning is necessary or not, these two steps are going to determine when you do industrial simulation, when you carry out experiments, and we find out that there is large differences between the two. In that case, we will tune the mathematical model, introduce some such factors, adjust the heat transfer coefficient, adjust the thermal conductivity value, manipulate the source term in order to get better correspondence with the experimental measurement, and this purple color line shows that now with model tuning I have been able to get the trend of the actual variation fairly realistically. So I say it is an industrially now tuned mathematical model, and this mathematical model is now all set for implementation of the software for doing process analysis, design, optimization, whatever you would say or consider. Now, coming back to this particular issue, so I have how the models are formulated, that has been discussed. Now we understand that in many cases tuning of the model is going to be necessary. I want to elaborate this. Now there are many cases when we can formulate the equations exactly. For example, you all know that if I have a pipe flow problem, flow of fluid through a pipe, I can write the exact equation. I can write the exact boundary conditions. Absolutely no problem. I can get an analytical solution, and in that case I will find out that analytical or numerical solutions will match exactly with the experimental observation. Suppose I measure the velocity with the laser Doppler velocity, will match exactly with the experimental observation. Suppose I measure the velocity with the laser Doppler velocimeter, if it is a transparent tube, then I can measure the velocity with the EIV. I can measure the velocity with a hot film anemometer. I can compare with my numerical model, fully developed flow through a pipe. There is going to be not even a little difference between prediction and experiment. Prediction and experiment will match in toto. There no question of many model tuning comes. So therefore we can see that there are certain physical situations for which we can formulate the problem exactly. Okay, we can write down the equation correctly, we can write down the governing equations correctly, and there will be no problem as far as matching of prediction and experiments are concerned. So this is the first category of the problem. The second category of the problem is that where our understanding is not complete. Okay, so therefore many idealizations and approximations will go in model building. In that case, what happens, we will invariably expect that the model predictions and experimental observations. In that case, what happens? We will invariably expect that the model predictions and experimental observations will not match. Because our understanding of the physical scenario or physics of the process is not totally clear. For example, how does, when you inject gases, argon gas through the ladle, how a gas envelope forms? Around the origin. How it devolves into a fluid, how it breaks up, the big gas envelope breaks up into a number of bubbles, how the bubbles coalesces during their rise or disintegrate. This complete picture, we understand it reasonably, but the picture is not absolutely clear. So therefore, if I have to write model equations for this particular phenomenon, that the injection of gas, its formation of a big gas envelope, its break up into a number of bubbles, the coalescence of the number of bubbles into a bigger one, And all this phenomena, incorporating all this phenomena, if I have to write down the model for bubble size distribution, you will see that there is going to be a lot of idealization. In the secondary cooling zone of the continuous transfer, for example, if I have to say that, well, I want to develop a mathematical model for heat transfer coefficient in the first. There also we will see that yes, our understanding is far from being complete, because the impinging, you have a nozzle through which you have spray mist which is coming. It's a spray mist is what? It is air and water. So the spray mist comes, and this is the surface of the billet, and the spray mist impinges on the surface, and in the process it breaks down into number of droplets. It impinges on the hot surface, removes heat from the hot surface. So therefore, this process is extremely complex, and our understanding of droplet formation, breaking of the continuous stream into droplets, impingement of the droplets, evaporation, etc. At the surface, these are far from being complete. So as a result of which, when we try to formulate problems for this scenario, we will see that considerable amount of idealization and approximations will go in the model building. Unfortunately, steel making processes fall in the second category. Steel making, mathematical models of steel making are not going to be like pipe flow problems, that we can write down the equation exactly, that we can formulate the governing boundary conditions exactly. No, we will never have this kind of scenario in steel making because of the inherent because of the nature of the manufacturing technique. So therefore, it is understood, it is to be appreciated at this stage that when you build models for steel making processes, inherent problems, inherent idealizations are going to be there in the initial conditions. Some deviation from 20%, 25% of what we people in industry today say that if your model can predict within plus minus 20%, 25% of what we see in the industry, you will consider your model to be reasonably good. So that is the kind of range or the tolerance we are given because of lack of complete understanding of the subject. Now, we can say that performance, of course, following tuning will in straightforward way applied. So, without this companion experiment, we will never know the extent of tuning which is necessary. So, therefore, I have been repeatedly telling that merely solving governing equations and boundary conditions are not enough. This is called as a black box modeling. We have to have companion measurements in order to demonstrate the applicability or suitability of the mathematical model that we have been able to formulate. Now, let us look at the issues of uncertainty. As we have tried to indicate so far that the formulation of the model as well as the boundary conditions are going to give rise to some kind of uncertainty. Now, I will explain very briefly the context in the context of uncertainty in boundary condition. For example, if I have to model that scenario, which again I will draw here, okay. So there you may require that what is the ambient temperature. Now I can say that, well, the surrounding temperature is 1200 degrees centigrade and it is radiation which is giving heat to the slab. This radiation, surrounding temperature is 1200 degrees centigrade. And it is radiation which is giving heat to the slab. To its surface. Okay. Now, therefore, somehow I have to know what is the final temperature. So I have to have a measuring devices, and based on that, I will be knowing that what is the temperature. So there is going to be some amount of uncertainty when we rely on empirical measurements in the boundary. This surrounding temperature, when I am solving for temperature within the solid, surrounding temperature is needed as a boundary condition. And how do you know the surrounding temperature? By carrying out certain experiments or with some temperature controller or pyrometer, etc. So therefore, those measurement devices also have some inherent error. So therefore, certain amount of error and uncertainty is with this. Similarly, when you're talking of heat, heat flow, modeling of heat transfer in the melt, and then we require that, well, what is the difference in temperature here is a result of Q loss. So we must know that at what rate through the refractory lining in the ladle heat is being lost outside. How can you know this? There is no way of determining it theoretically. We have to put a probe here. Either we measure temperature or we directly measure the heat flux through a heat flux transducer and then tell you that, well, this is the rate at which the heat is being lost. So when I write the governing differential equation for heat flow within the melt, these informations will appear as boundary conditions for the governing equation. Where from these boundary conditions will be given which the heat is. We directly measure the heat flux through a heat flux it theoretically. We have to put a probe here. Either we measure temperature or we directly measure the heat flux through a heat flux transducer and then tell you we're talking of heat flow, modeling of heat transfer in the melt, and then we require that, well, what is the difference in temperature here is a result of Q loss. So we must know that at what rate through the refractory lining in the ladle heat is being lost outside. How can you know this? There is no way of determining it theoretically. We have to put a probe here. Either we measure temperature or we directly measure the heat flux through a heat flux transducer and we have to put a probe here. Either we measure temperature or we directly measure the heat flux through a heat flux transducer and then tell you that, well, this is the rate at which the heat is being lost. So when I write the governing differential equation for heat flow within the melt, these informations will appear as boundary conditions for the governing equation. Where from these boundary conditions will be given, these will be directly based on its. So that's why when we measure these quantities, either the either the temperature within the furnace or the rate of heat loss through the steel shell in a ladle, these are all empirically determined parameters. So they are all prone to error because of inherent problem. associated with the measuring devices. So, we understand that the uncertainties are going to be because of number one, uncertainties in formulating the governing equation. Correct. That I have explained. We can have also uncertainties that we do not know. For example, the thermophysical properties of the system. Thermal conductivity, how it varies as a function of temperature and composition, we may not be exactly knowing. Okay? If we do not know, in that case we can say that well, the properties of the system are not known. High temperature properties and kinetic data are not always available, so they also bring in certain amount. So uncertainty in boundary condition, uncertainty in governing equation, uncertainty in high temperature properties and kinetic data are the major sources of such uncertainty in boundary condition. Are not always available, so they also bring in certain amount. So uncertainty in boundary condition, uncertainty in governing equation, uncertainty in high temperature properties and kinetic data are the major sources of such. Okay, that's the difference that you're seeing here. So these three can be considered to be the main reasons. We must understand also the numerical methods are also prone to some error. But eventually, when you hit that grid independent solution, then that can be forgotten, or we may not consider that, because grid independent solution have to be identical, but certain numerical techniques, if you don't take precautions, can give you some erroneous results also. So numerical error is also one reason. So we have to have a robust numerical method in order to derive solution from the governing equation. Now, I have written the heat conduction equation very clearly. How do you formulate these equations? So, having understood, let us go back to this particular issue. Having said that I want to find out the temperature within the solid, then I have to write down it. I understand that is the thermal energy conservation. Because I know that the temperature at a point within the liquefaction is because of the heat which is being received, and the flow of heat within the solid itself, it is governed by that. So it is basically a conservation Okay, the rate of change of temperature at this particular point is a function of the rate at which the heat is being lost, heat is coming from the ambient to the surface, and I should be able to write an equation for this. So this is going to be an energy conservation equation. Now the question is, how do I write those equations? I mean, do we every time derive an equation from the control volume based approach? For example, you have seen Navier-Stokes equation, for example, you know Fourier's equation or Laplace equation. So how do you derive those equations? We take an elementary control volume, and in elementary control volume we can say that, well, to this I can say heat is coming in, heat is going out. So this is x, y, and z direction, and then we have heat which is coming in this particular direction, leaving in this particular direction. Heat which is coming in this direction. So the net rate at which heat content of this control volume increases or changes is a function of the net flux of heat along the heat. So I can set up an elementary control volume, and then I can find out that what is the characteristic conservation equation for this particular control volume. Imagine if I take this control volume to be one of the phase merging with the boundary, then that's how through the boundary control volume I will have the boundary information getting into the calculation domain. This may be an internal control volume, okay, and within an internal control volume I know it is the conduction of heat. So therefore I would say conduction of heat along x direction, conduction of heat out along x direction, conduction of heat along y direction, conduction of heat out along y direction, and so on. So because this is an internal control volume, and one of these surfaces can very well become the boundary surface. Okay, once the control volume is located here, and through that particular surface we will have the boundary information getting in the system. So one way of deriving the model equation is that we set up the control volume, formulate the governing equation, and whatever equation I have written as model equation is that the boundary information is given. So one way of deriving the model equation is that we set up the control volume, formulate the governing equation, and whatever equation I have written earlier, that can be derived very easily by control volume formulation. But for every problem, it is not justified to write down the control volume formulation and derive the equations, because I am not the first person to investigate heat conduction phenomena. There are innumerable other people who have studied heat conduction phenomena. These equations are documented in literature. These equations are documented, which I have written, for example. So I now write it in a little bit conservative. Divergent K gradient T plus C. So if you expand it in 3 dimension, you get the derivative, second order derivative along x, second order derivative along y, second order derivative. So these equations are well documented in the literature. Okay. So I can, once I understand the phenomena, I can pick up that particular equation from the previous one. At the most, I can examine that am I not perhaps blindly copying this equation? Is the equation dimensionally consistent? Is the equation correct? Is the equation wrong? So how can I pick up? There are innumerable equations of heat conduction. I say two-dimensional steady state, two-dimensional in cylindrical polar coordinate, three-dimensional in Cartesian coordinate, one-dimensional in spherical coordinate. So there are a lot of heat conduction equations that is in function. So how do I pick up the right equation? Which is and that is dictated by the conceptual model. And the concept
This is the largest slice of pizza in the entire world. Look how long it is. This pizza is literally 6 feet and taller than Carl.
My ego's shattered.
It just doesn't stop. It's still going. It's still going. It's so big. And this is Joey Chestnut, the fastest competitive eater in the entire world.
I'm hungry.
And not only does he hold the world record for hot dogs eaten, but he has so many more. Here's a quick montage of it. Not only does he hold the world record for hot dogs eaten, but he has so many more. Here's a quick
modeling itself, I am not able to see that what is the differential equation that I have to pick up from the literature so that I can altogether avoid this control volume formulation part. You can of course do this if you have time, but it is not necessary always. Okay, equations are available in the literature. You have to understand the physical scenario and then pick up. So there you say that there are building blocks available. So this is called, I would say, a heat conduction building block. So in heat conduction building block, what I'm going to have? I'm going to have heat conduction. In 3 dimension in spherical coordinate, heat conduction in 3 dimension in spherical coordinate, heat conduction in 3 dimension in Cartesian. Steady state. Similarly, I can have 3 other equations: unsteady state heat conduction in Cartesian coordinate, unsteady state 3-dimensional heat conduction in cylindrical polar coordinate, unsteady state 3-dimensional equation in spherical coordinate. So I have a series of equations in the heat conduction module or heat conduction building block, and I'm going to pick up with my own understanding. So therefore, we have summarized various building blocks necessary for mathematical simulation of steam. And these building blocks could be, one could be a fluid flow building block. So building blocks. What does the building blocks contain? Building blocks contain the differential equations or the. What does the building blocks contain? Building blocks contain the differential equations or the mathematical models of fluid flow. Why so many mathematical models? Because they contain a set of equations written in unsteady state mode or steady state mode, written in 2 dimension or 3 dimension, written in various coordinate systems. So that's why we have a range of choice available to us. We have to only understand that, well, we got to simulate the fluid flow, so therefore we have to go to the fluid flow building block and pick up the equation. We can have building block for turbulence also. There may be various types of turbulence model. Okay, as I've mentioned earlier in one of the lectures. So we can have various kinds of models. You have a choice there. What kind of a model you would like to use? Okay, so according to that, you can pick up the right equation that is applicable to your case. You can have heat conduction module, which I have just now discussed. And the counterpart, you can have mass diffusion also. You can have convection diffusion. You can have magnetohydrodynamics. There are all modules or building blocks available to us. And there are many such building blocks. You can have magnetohydrodynamics. There are all modules or building blocks available to us. And there are many such building blocks. So we have to understand the problem. We have to see what we are trying to model, and accordingly. So I want to, for example, I'll just illustrate. I want to model heat flow within a ladle. Now, I understand that in the ladle there may be some fluid flow involved because the transport of heat. This is a liquid. So within the liquid or in the melt, transport of heat is due to convection and so within the liquid or in the melt, transport of heat is due to convection and diffusion. Diffusion means it is heat conduction here. So diffusion is a generic term for all. We have momentum diffusion, we have mass diffusion, we have heat diffusion. Okay, so therefore heat diffusion is heat conduction, momentum diffusion is viscous diffusion, and mass diffusion is mass diffusion. Okay, so the movement of temperature, the heat will flow from one point to another point because of the presence of the fluid flow as well as the diffusion or heat conduction. So therefore I will So, the movement of temperature, the heat will flow from one point to another point because of presence of the fluid flow. As well as the diffusion or heat conduction. So therefore, I will say that I need not a heat conduction module but a convection diffusion of heat or mass. Presence of the fluid flow as well as the diffusion or heat conduction itself. Because of presence of the fluid flow as well as the diffusion or heat conduction. So therefore, I will say that I need not a heat conduction module but a convection diffusion of heat or mass. This is the building block, but a convection diffusion of heat. I will say that I need not a heat conduction module but a convection diffusion of heat or mass. This is the building block. These are one and the same equations, one and the same type of equations, because temperature and species are scalar quantities. So therefore, I can say that I can pick up this and then I will have to model, because I am talking of convective heat transport. This convective heat transport I will not be able to address unless I know fluid flow. So therefore, fluid flow I will have to use, and if the flow is turbulence, in that case I will. So these three building blocks will formulate the mathematical framework or provide the mathematical framework for prediction of temperature. Of course, talk of this convection diffusion of heat, in that case we will require thermal boundary conditions. Right? So all boundary conditions that we prescribe, whatever is necessary, but as far as writing the governing equations are concerned, we will select fluid flow, we will select turbulence, we will select convection diffusion, and then identify what is the dimensionality problem, whether it is a steady state or not. So from the innumerable number of equations that are available under each of these categories, we have to pick up the right equation. So the last point that I want to make here is we have many phenomena which we may have to calculate simultaneously. We may have to calculate, for example, electromagnetically driven flows. For example, if you want to simulate fluid dynamics in continuous casting slabs, where we may have electromagnetic braking, electromagnetic stirring. So we may have fluid flow, turbulence, heat transfer. Many phenomena can be simultaneously or interrelated. Okay. We have multi-phase flows. We are injecting gases. We have slag metal mixing. We have heat loss. Have good state processing operations. You may have. So we are talking about solving a series of nonlinear partial differential equations. The equation is not going to be only one. There will be several, tens or 12 of such equations. These equations are interlinked with one another. These equations are non-linear, and there may be the boundary conditions may be complex. Non-linear boundary conditions. So, solving this equation is a horrendously complex task. And if you have to write a computer program, this is going to take many months before you can write the computer program to solve this set of equations and derive a meaningful result of comparison. So, what is the option? There comes the role of commercial software. So, today, engineering training, and particularly people who are involved with steel making, the process modeling, they have to know that what are the commercial software platforms available which they can effectively use to solve it. So your job ends at formulating the problem, okay, and then you configure the problem with the aid of commercial software. The solution, when I talk of solutions, the solution essentially encompasses writing of the equation, then coding the equation in a computer, and then getting the number. So this coding part can be totally eliminated if you can resort to commercial software. And two commercial softwares which are very popular today are Fluent and COMSOL. So most of the mechanistic models that we use can be solved, mechanistic models for steel making can be solved by using Fluent. Fluent has all these modules, all these building blocks built up. You have to just say that it is three-dimensional, unsteady state. The results in particularly no time, and then you can post-process. That means you can plot and you can scientifically visualize the results. How does the temperature is changing as a function of time, or how does the velocity is changing as a function of time. Obtain useful information of the process. So to conclude the discussion on physical and mathematical modeling, complete picture. To draw a vertex triangle, and vertex lies the plant scale trial. Well, I would say that if you draw a vertex triangle And then in this vertex lies the physical model. In this vertex lies the mathematical model. In this vertex lies the plant scale trial. And there is the truth physical model. In this vertex lies the plant scale trial. And there is the truth. And so, in order to hit the truth, you have to have these three components. And then only possibly you can do process analysis, process design, optimization. Correct. So, any comprehensive investigation on steel making must therefore embody physical modeling, mathematical modeling, and plant scale in different proportions depending on your resources. And when these three are combined together, you with this comprehensive.